Out there in the endless dark, between the stars we see and the ones we can only dream of, the universe whispers secrets we have yet to fully understand. It's a place of breathtaking scale and profound mystery, where light takes millions of years just to reach our eyes, carrying stories from a past so distant it challenges imagination. And sometimes, amid that cosmic silence, something extraordinary happens, a signal, sharp and sudden, cutting through the emptiness like a voice calling out from the void. These aren't the gentle hum of distant galaxies or the predictable rhythms of pulsars. These are bursts of energy so powerful, so brief, and so puzzling that they've captivated astronomers and dreamers alike, hinting at phenomena beyond our current understanding. For decades, we've trained our most advanced instruments on the sky, listening intently for any sign that we're not alone in the vastness, or perhaps for clues about the extreme physics playing out in the farthest reaches of space. And what we've found is both thrilling and deeply mysterious. Strange, repeating radio waves, one-time blasts of energy with no obvious source, and signals that behave in ways that defy easy explanation. Each one is a cosmic riddle, a piece of a puzzle that spans light years and challenges everything we think we know about the universe, from the famous wow signal that vanished as mysteriously as it appeared, to fast radio bursts that pack more energy than our sun emits in decades. These aren't just scientific curiosities, they're invitations to wonder, to explore, and to question. In this video, we're diving deep into 25 of the most fascinating and mysterious signals ever detected from deep space. We'll travel from the far edges of our own galaxy to distant cosmic structures, unpacking the stories behind these enigmatic messages and the incredible efforts to decode them. You'll discover why some signals have researchers considering possibilities as wild as alien civilizations, while others point to cataclysmic astrophysical events we're only beginning to comprehend. This is a journey into the unknown, a chance to stand beside the scientists and stargazers who look up at the night sky and dare to ask, what if? So settle in, open your mind to the possibilities, and let's explore the mysteries hidden in the echoes of the cosmos. Our journey into the cosmic unknown begins not in the distant reaches of another galaxy, but right here in our own cosmic backyard, with a signal so iconic that its very name captures the sheer astonishment it provoked. It was a warm summer evening on August 15, 1977, at Ohio State University's Big Ear radio telescope. This massive instrument, essentially a sprawling aluminum sheet designed to focus cosmic radio waves, was methodically scanning the sky as part of the ongoing search for extraterrestrial intelligence, or SETI. Its operation was largely automated, with data printing out on long, continuous sheets of paper for astronomers to review later. For days, even weeks, these printouts typically revealed nothing more than the usual, gentle background static of the universe. But on this particular night, the telescope's steady gaze passed through the constellation Sagittarius, and something extraordinary happened. The signal that roared into the Big Ear receiver was unlike anything in the background noise. It was a powerful, focused burst of radio waves at exactly 1420 MHz. This frequency is no random number. It's a sacred channel in the science of SETI, known as the hydrogen line. Hydrogen is the most abundant element in the universe, and scientists have long hypothesized that any advanced civilization attempting to broadcast its presence might use this universal, natural radio frequency as a sort of cosmic hailing channel. The signal grew rapidly in intensity, peaked for a full 72 seconds, the exact duration it would take for such a source to pass through the Big Ear's fixed field of view, and then vanished just as sharply as it had appeared. Days later, a young volunteer named Jerry Amon was poring over the data printouts. As his eyes scanned the columns of alphanumeric characters representing signal strength, one sequence in particular made him stop dead. Where most readings were simple numbers or a single digit, one string stood out, 6EQUJ5. This was the computer's way of representing an off-the-charts signal intensity. The characters U and J represented levels of power so intense they were rarely, if ever, seen from a natural cosmic source. Stunned, Jerry Amon circled the sequence in red pen and beside it wrote a single, now legendary word, wow. That original computer printout with its red ink notation has become a holy grail of sorts for astronomers and enthusiasts. The signal's characteristics are what make it so compelling. It was narrowband, meaning it was concentrated on one specific frequency, much like a radio station. Natural cosmic objects like pulsars or quasars typically emit a broad spectrum of radio noise. This was a clean, artificial sounding whistle in the cosmic static. Its 72-second duration and bell-shaped curve perfectly matched the telescope's operation, pointing to a source just beyond our solar system, but not from a distant galaxy. Despite its incredible strength, the WOW signal was a one-hit wonder. Decades of follow-up observations using far more sensitive equipment have scoured that same patch of sky in Sagittarius. The result has been a profound and enduring silence. Nothing like it has ever been detected again from that location. This singular nature is the heart of the mystery. Could it have been a secret military transmission or a reflection from a piece of space junk? These possibilities have been largely ruled out, as such interference would not have the precise frequency characteristics or would likely have been detected again. The signal's properties point overwhelmingly to an origin beyond Earth. So if it wasn't us, what was it? The leading natural explanations, like a comet, have also failed to hold up under scrutiny. The absence of a repeat signal is its most tantalizing and frustrating quality. It's as if the universe whispered a single, perfect word in our ear and then refused to ever speak again. For that brief moment in 1977, it felt like we might not be alone. The WOW signal remains the gold standard, the single best candidate for a signal that could have originated from an intelligent civilization somewhere out in the vast dark, a fleeting hello that continues to echo through the decades. If the WOW signal was a fleeting, one-time cosmic shout, then the story of FRB 121102 is the universe deciding to have a full, unpredictable conversation with itself. Discovered in 2012 by the massive Arecibo radio telescope in Puerto Rico, this wasn't just another brief blip on the radar. Initial observations pegged it as a fascinating but perhaps singular event, another entry in the growing catalogue of mysterious fast radio bursts. These FRBs, as they're known, are incredibly powerful eruptions of cosmic radio waves that last for just milliseconds. Yet in that blink of an eye, they can release more energy than our sun does in 80 years. For a long time, every single one detected was a one-off event, leading most scientists to believe they were caused by catastrophic, universe-shattering explosions. The final, desperate signals of stars being torn apart by black holes or neutron stars colliding in unimaginably violent mergers. These were events so final that they could, by definition, only happen once. Then, in 2015, everything changed. Astronomers pointed the Arecibo dish back at the location of FRB 121102, and to their absolute astonishment, they detected another burst. And then another, and then several more. This wasn't a dying star's last gasp. This was a source that was very much alive and actively, if sporadically, repeating its performance. This single discovery sent shockwaves through the astrophysics community. By proving that at least some FRBs could occur more than once, it completely dismantled the leading cataclysmic models. You can't have a star explode over and over again. Suddenly, the door was flung wide open to a whole new realm of possibilities involving objects that could survive these immense eruptions and produce them repeatedly. The next great leap was figuring out where this mysterious repeater was calling from. Pinpointing the origin of a millisecond burst of radio waves from 3 billion light-years away is one of astronomy's most daunting challenges. It required a global effort combining the immense resolving power of the Very Large Array Radio Telescope in New Mexico with other observatories around the world. After a painstaking campaign, they succeeded, tracing the signal's origin not to a large, majestic spiral galaxy like our own Milky Way, but to a small, unassuming dwarf galaxy. This was another crucial clue. This tiny galaxy was actively forming new stars at a prodigious rate, suggesting its environment was rich with the young, volatile stellar objects that could be the engines for such tremendous bursts of energy. But the behavior of FRB 121102 is perhaps its most bizarre characteristic. It doesn't repeat on a schedule or in a predictable pattern. Instead, it goes through frenetic periods of activity, firing off numerous bursts in a short amount of time, sometimes even multiple bursts in a single hour, only to fall completely silent for weeks or months. It's as erratic and unpredictable as a sleeping dragon, occasionally waking to roar before dozing off again. This erratic repetition has solidified its status as the most studied and most mysterious FRB, a celestial beacon that forces us to consider extraordinary origins, from highly magnetized, spinning neutron stars known as magnetars to speculative technologies of advanced civilizations. It taught us that the universe is not only stranger than we imagine, but that it is capable of creating phenomena that repeat, persist, and challenge our understanding of cosmic physics on a daily basis. While the erratic chatter of FRB 121102 rewrote the rulebook on what was possible, another signal would soon present a mystery of an entirely different sort, one governed not by chaotic randomness, but by a clockwork precision that seemed almost artificial. In June of 2019, the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, telescope detected a new repeating fast radio burst, designated FRB 180916. Like its famous predecessor, it repeated, but this one did something that left astronomers utterly speechless. It followed a schedule. This wasn't a vague pattern or a statistical coincidence. FRB 180916 operates on a near-perfect cycle of 16.35 days. For roughly 4 days, it enters an active window, firing off multiple bursts, sometimes as often as once an hour. Then, as if a cosmic switch is flipped, it falls completely and predictably silent for the next 12.35 days. This cycle repeats with unwavering regularity, a metronome ticking across 500 million light-years of space. Pinpointing its origin added another layer of fascination. It wasn't in a distant, anonymous void, but in a relatively nearby spiral galaxy, a familiar stellar neighborhood similar to our own Milky Way, and crucially, it was traced to a specific region within that galaxy, a region alive with the formation of massive new stars. This precise periodicity is the key to its mystery. In all of astronomy, predictable cycles almost always point to one thing: orbital motion. The leading theory suggests we are not looking at a solitary object, but a binary system, a pair of cosmic dancers locked in a gravitational embrace. Imagine a highly magnetized neutron star, a magnetar, which is already a prime suspect for generating these immense energies. This magnetar could be in orbit around another massive object, perhaps a massive star or even a black hole. For a few days in its orbit, it passes through a specific region, like a dense cloud of gas and dust flowing from its companion star. This environment could act as a trigger, allowing the magnetar to unleash its powerful radio burst. Then, as it continues along its orbital path, it moves out of this triggering zone, and the bursts cease for the next 12 days until the cycle begins anew. This elegant model provides a stunningly plausible natural explanation, but its implications are profound. If correct, it doesn't just solve one puzzle. It gives us a specific, testable blueprint for the kind of environment that can manufacture these bizarre signals. It suggests that the recipe for a repeating FRB might require a very particular stellar cocktail, a powerful central engine and a specific, dynamic environment it regularly passes through. This moves the mystery from the abstract, what could possibly do this, to the specific, allowing astronomers to search for similar binary systems and test this model against new discoveries. The existence of such a precise cycle also allows for incredibly efficient observation. Instead of staring endlessly at a silent patch of sky, telescopes around the world can be pointed at FRB 1809-16 during its active window, dramatically increasing the chances of catching it in the act and studying its bursts in exquisite detail. It transformed this burst from a cosmic anomaly into a reliable laboratory, offering a structured glimpse into the heart of one of the universe's most energetic and enigmatic phenomena. While the rhythmic pulse of FRB 1809-16 offered a tantalizing pattern to study, the very existence of such phenomena hinged on a single, chance discovery that was initially so unbelievable it was almost dismissed entirely. The story of fast radio bursts doesn't begin with a state-of-the-art telescope or a planned survey, but with a young astronomer named Duncan Lorimer and his student David Narkevic sifting through old data. The year was 2007, and they were analyzing observations from the Parkes Radio Telescope in Australia, recorded 6 years prior in 2001. The data was from a survey of the Magellanic Clouds, 2 small satellite galaxies orbiting our Milky Way, and their task was to search for new pulsars, the rapidly spinning, dense cores of dead stars that emit regular radio pulses. But buried in that mountain of ones and zeros was something that defied all known categories. What they found was a burst of radio waves so intense it saturated the telescope's receiver. Lasting a mere 5 milliseconds faster than the blink of an eye, this spike of energy was unlike the steady, repeating beat of a pulsar. It was a singular, colossal explosion of power. When they calculated its strength and its apparent distance, the numbers were staggering. This was not a local event. The signal's characteristics indicated it had traveled from far beyond our own galaxy, from a source potentially billions of light years away. For a burst to be that bright from such an unimaginable distance meant the energy released was almost incomprehensible. In those 5 milliseconds, the source emitted as much energy as the sun does over 80 years. It was a true cosmic transient, a one-off event of cataclysmic proportions. Presenting such a finding to the scientific community, however, was met with deep and understandable skepticism. The signal was so powerful and so brief that many wondered if it was even real. Could it have been a terrestrial glitch, a burst of interference from a passing satellite, or even a microwave oven being opened prematurely at the observatory's facility? The Parkes telescope had a known history of picking up local radio frequency interference, jokingly referred to as puritans, after a mythical stag that casts a human shadow. For years, the Lorimer burst, as it became known, stood alone as an unsolved anomaly, a ghost in the machine that many believed was probably just an instrument error or a human-made signal masquerading as something cosmic. Its validation as a genuine astrophysical phenomenon was a slow process, achieved not by finding the burst again, but by the painstaking work of ruling out every other possible explanation. Researchers meticulously eliminated potential sources of interference and reanalyzed the data. The crucial breakthrough came years later when other, similar bursts were finally discovered by other telescopes, confirming that what Lorimer had found was not a fluke but the first example of an entirely new class of cosmic event. This single 5 millisecond blip opened up a whole new field of astronomy. It forced us to confront the reality that the universe is filled with incredibly brief, incredibly violent eruptions that had gone completely unnoticed. The Lorimer burst was the first clue, the catalyst that launched a global hunt to understand these mysterious messages, proving that sometimes the most profound discoveries are hidden not in the future, but in the archives of the past. Amidst the cataclysmic energy of fast radio bursts, the search for a very different kind of signal has continued, one not born from stellar explosions, but perhaps from an intelligent mind. This brings us to one of the most enduring and debated candidates in the history of SETI, a signal that, for a brief period, seemed to tick every box on the checklist for a potential hello from another world. Its designation is a string of characters only an astronomer could love, SHB02+14a. Detected in 2003 by the SETI at Home project, this signal represents a fascinating and frustrating chapter in the quest to find extraterrestrial intelligence, precisely because it was so perfectly peculiar. SETI at Home was a revolutionary concept. Instead of relying on a single large telescope, it harnessed the distributed computing power of millions of volunteers worldwide. People would run a screensaver program on their personal computers that automatically downloaded and analyzed small chunks of radio telescope data from the Arecibo Observatory, searching for any narrowband signal that stood out from the cosmic background noise. It was a cosmic needle in a haystack search, and for years the project found countless needles that turned out to be human-made interference. But SHB02+14a was different. It was detected not once but 3 separate times, each instance lasting less than a minute. Its frequency was centered on 1420 MHz, the famous hydrogen line, a universal frequency that scientists have long theorized would be a logical choice for any civilization attempting to make contact. Even more intriguing was its drift rate. A radio signal transmitted from a planet orbiting a distant star would not appear as a perfect, unchanging tone to us. Because that planet would be rotating and orbiting its star, the signal would appear to slightly change in frequency as it moves towards and then away from Earth, much like the pitch of a siren changes as an ambulance races past. This change is measured as a drift rate. The drift rate of SHB02+14a was measured at between -8 and -10 Hz per second, a value that is perfectly consistent with what we would expect from a transmitter located on a planet similar to Earth. It was as if the signal was doing its best to impersonate exactly what scientists had been hoping to find for decades. But here is where the mystery deepens into controversy. When astronomers pointed optical telescopes toward the patch of sky where the signal seemed to originate between the constellations Pisces and Aries, they found nothing. The region appeared to be virtually empty. There was no visible star system, no galaxy, no obvious source of any kind within 1,000 light-years. This void is the central paradox of SHB02+14a. How could a signal with such a seemingly artificial signature, a narrowband transmission on the hydrogen line with a plausible drift rate, be coming from a place with no visible cosmic landmarks? Skeptics argued this was the most definitive evidence that the signal was, in fact, an extremely clever and persistent form of radio frequency interference, perhaps from a secret military experiment or a piece of orbiting technology that mimicked the expected drift rate by chance. Proponents, however, offered a more thrilling possibility. What if the source is not in deep space but much closer? The signal's apparent lack of parallax, meaning it didn't shift position relative to background stars, suggested it was not within our solar system. But it could theoretically originate from a great distance, perhaps from a spacecraft or probe from an advanced civilization, a concept that moves from science fiction into a remote scientific possibility. The true legacy of SHB02+14 is not necessarily that it was our first contact, but that it perfectly encapsulates the immense challenge of modern SETI. It is a signal that is at once both the best and worst candidate. It possesses several hallmarks of an artificial broadcast, yet it emerges from a celestial desert, offering no target for follow-up. It is a whisper that was heard 3 times and then vanished forever, leaving behind no evidence to prove or disprove its extraordinary potential. It remains a tantalizing enigma, a reminder that in the search for cosmic company, the most intriguing answers are often those that raise the most profound and unanswerable questions. While the search for a signal from the stars often spans billions of light years, sometimes the most captivating mysteries appear to originate startlingly close to home. In the autumn of 2019, astronomers working with the Breakthrough Listen project detected a signal that seemed almost too good to be true. It wasn't from a distant, anonymous galaxy, but from the direction of our nearest stellar neighbor, Proxima Centauri, a mere 4.2 light-years away. This red dwarf star is already a prime target in the hunt for habitable worlds, as it hosts at least 2 known planets, one of which, Proxima Centauri b, orbits within the star's habitable zone, the region where temperatures could allow for liquid water to exist on its surface. The detection of a potential technosignature from this specific system sent a palpable wave of excitement through the scientific community. The signal was designated BLC-1 for Breakthrough Listen Candidate 1. What made BLC-1 so compelling were its impeccable characteristics. It was a narrowband signal concentrated at 982 MHz, a frequency typically quiet and free from both natural cosmic noise and common human-made interference like satellites or aircraft. Natural astrophysical phenomena like pulsars or stellar flares emit radio waves across a broad spectrum of frequencies. This signal was a clean, pure tone, precisely the kind of signature you would expect from an intentional transmitter. Furthermore, the signal exhibited a distinct drift rate. Its frequency appeared to change slowly over time. This is a crucial clue, as it mimics the effect of a transmitter located on the surface of a rotating planet, its movement causing the frequency of its broadcast to shift slightly, much like the changing pitch of a passing ambulance siren. For a brief, thrilling period, BLC-1 checked every box on the list of what an authentic alien signal might look like. The initial discovery was made using the Parkes Marion radio telescope in Australia, which was observing Proxima Centauri as part of a broader survey. The signal was detected during multiple observation sessions over several hours, but it was never heard again in subsequent dedicated searches. This fleeting nature only added to its mystique. The team behind the discovery did not immediately announce it to the world. Instead, they embarked on a meticulous, year-long analysis, determined to rule out every possible alternative explanation before even whispering the word alien. This cautious approach is a hallmark of modern SETI, born from decades of previous false alarms and the desire for scientific rigor above sensationalism. The eventual conclusion, however, was a sobering lesson in the immense challenge of this work. The meticulous investigation revealed that while the signal itself was real, its origin was almost certainly not Proxima Centauri. The most likely explanation, though it could never be proven with absolute certainty, was that BLC-1 was a form of intermodulation distortion. This is a type of interference that can occur when 2 or more human-made radio signals, perhaps from a nearby cell phone, a piece of electronic equipment, or even a passing car, mixed together inside the sensitive electronics of the receiver itself, accidentally creating a new, artificial signal that possesses all the seemingly perfect properties of a technosignature. The signal's drift rate, once so promising, was likely just a Chinese letter, a random artifact of this electronic mixing process. BLC-1 was not a message from Proxima Centauri b. It was a ghost in the machine, a cosmic prank played by our own technology. The story of BLC-1 is a powerful parable for the modern search for extraterrestrial intelligence. It underscores the razor's edge that researchers must walk between boundless optimism and rigorous skepticism. It demonstrated that our most advanced equipment is now so sensitive that it can be fooled by incredibly subtle and complex forms of human-generated radio frequency pollution that didn't even exist a few decades ago. Yet, despite the ultimate letdown, the process was far from a failure. The detection and thorough analysis of BLC-1 refined the protocols for future signal verification, making the entire scientific endeavor stronger and more prepared for the day when a signal refuses to be explained away. It proved that we have the tools and the discipline to find a needle in a cosmic haystack, even if the first few needles we pull out turn out to be from the shed right next door. For years, the sources of fast radio bursts were phantoms, their incredible power only magnified by their incomprehensible distance. Locating one felt like trying to pinpoint a specific firefly blinking in a city on the other side of the planet. That all changed with a burst detected on January 20th, 2020, a signal that would rewrite the narrative not by its strength or its pattern, but by its stunning proximity. Designated FRB 2020-00120E, this burst didn't hail from a distant dwarf galaxy billions of light-years away. Follow-up observations by a network of telescopes revealed its origin was shockingly close to home, right inside our own Milky Way galaxy, a mere 12 million light-years from Earth, emanating from a highly magnetized neutron star in the constellation Ursa Major. This proximity was an absolute game-changer. For the first time, astronomers weren't just seeing the brilliant flash of the burst itself. They could train the full might of their observational power on the object responsible for it. The source was identified as a magnetar, a specific type of neutron star with a magnetic field so intensely powerful it defies earthly comparison. To put it in perspective, a magnetar's magnetic field is a quadrillion times stronger than Earth's, strong enough to violently distort the atoms in your body from thousands of miles away. These objects are the cosmic equivalent of permanent seismic zones with crusts under unimaginable strain, capable of producing starquakes and releasing titanic flares of energy. FRB 2020-00120E provided the long-sought-after smoking gun, directly linking at least one type of fast radio burst to the extreme physics of these magnetic monsters. With the source identified, the focus shifted from what to how. How could a single city-sized object generate a millisecond burst that rivals the energy output of an entire sun for decades? The detailed study allowed scientists to move beyond speculation and start building concrete models. The leading theory involves a dramatic event known as a magnetar flare. Imagine the star's crust, under immense strain from its own twisting magnetic field, suddenly cracking in a starquake. This seismic event releases a massive amount of energy, ejecting a cloud of electrified particles into the surrounding space. As this expanding cloud slams into the magnetar's own incredibly dense, magnetized environment, it creates a shockwave. It is within this violent maelstrom that the fast radio burst is thought to be born. The chaotic interactions in the shockwave accelerate particles to near light speed, and as they spiral along the magnetic field lines, they emit a coherent blast of radio waves, a lighthouse beam of energy focused and shot out across the galaxy. The detection of FRB 2020-00120E didn't just solve one mystery, it opened a new chapter in high-energy astrophysics. It strongly suggests that magnetars are a primary, if not the only, source for at least some types of FRBs. This single nearby event became a Rosetta Stone, providing the key to interpreting the thousands of more distant, fainter bursts we've detected. It suggests that the incredibly powerful, one-off bursts observed in other galaxies could be the signatures of even more colossal magnetar flares, while the repeating bursts might come from younger, more active magnetars going through frequent periods of eruption. This galactic neighbor gave us a front-row seat to one of the universe's most violent phenomena, transforming these enigmatic signals from abstract cosmic mysteries into understandable, albeit extreme, stellar events. Just as the universe seemed to be revealing some of its most powerful secrets, astronomers were forced to confront a humbling and far more earthly truth. Not every mystery originates in the cosmos. For years, the Parkes Radio Telescope in Australia, a workhorse in the search for pulsars and fast radio bursts, had been detecting its own set of bizarre signals. Dubbed Puritans after a mythical winged stag that casts a human shadow, these signals were frustratingly similar to the enigmatic FRBs. They were brief, intense bursts of radio waves that seemed to come from the sky above. Yet they possessed one peculiar characteristic that set them apart. They were only ever detected during daytime working hours and, even more strangely, always on weekdays. This was a glaring clue that pointed not to the heavens, but to something decidedly mundane happening right there on the observatory grounds. The scientific process of elimination became a grand, if slightly absurd, detective story. Researchers first had to rule out every possible natural and human-made source they could imagine. Could it be lightning from distant storms, atmospheric phenomena? They checked and double-checked. The signals seemed to come from a wide area of the sky, which initially suggested a distant, dispersed source. But the weekday-only pattern was a stubborn anomaly that cosmic events simply don't obey. The plot thickened when other radio telescopes around the world reported they had never detected a single Puritan, even when staring at the same patch of sky as Parkes. The evidence was mounting that the source was local, unique to that one facility. The hunt was on, transforming the observatory into a scene of a scientific whodunit. The breakthrough finally came when a new, more sensitive monitoring system was installed at the telescope. This system could detect radio frequency interference across a much wider range, and crucially, it recorded data with a timestamp precise to a fraction of a second. In early 2015, as researchers were analyzing new data, they caught a Puritan red-handed. At the exact moment the burst was recorded, the monitoring system also picked up a very familiar, very terrestrial signal across a broad range of frequencies. The mystery was solved not by looking up at the stars, but by looking toward the staff kitchen. The source was the observatory's microwave oven. The specific sequence of events was both hilarious and brilliant in its simplicity. A Puritan was not generated when the microwave was running. It was created in the split second someone grew impatient and opened the oven's door before the timer had finished and the magnetron had fully shut off. This premature opening allowed a blast of 2.4 GHz radiation, the standard frequency for heating water molecules, to escape directly upward, where it could then reflect off the metal surface of the observatory's massive dish and flood the receivers, mimicking an astrophysical event from deep space. The reason they only happened on weekdays was because that was when staff were present to heat up their lunches. The final, beautiful proof came when researchers deliberately recreated the event, producing a perfect Puritan on demand by opening the microwave door at just the right moment. The resolution of the Puritan mystery is a celebrated tale in astronomy, not as a story of failure, but as one of ultimate scientific rigor and humility. It underscores a critical lesson. Before claiming a discovery that shakes our understanding of the universe, we must first be absolutely certain the signal isn't coming from our own break room. It's a testament to the perseverance of the researchers who refuse to ignore an inconsistency, even a silly one, and whose diligent work ultimately allowed them to confidently distinguish between a cosmic event and a cosmic lunch. This meticulous process of eliminating the mundane is what gives us the confidence to believe in the truly extraordinary signals that remain. While the tale of the microwave oven taught us to look for answers close to home, the next signal on our list presented a puzzle that seemed to bridge the gap between the tantalizingly plausible and the frustratingly terrestrial. In the spring of 2015, the Rattan 600 radio telescope, a unique and massive cylindrical antenna nestled in the Caucasus Mountains of Russia, detected something extraordinary. The telescope was engaged in a sweeping survey of the sky, and as its gaze passed over the star system HD 164595, it recorded a powerful, singular radio burst at a frequency of 11 GHz. The signal, lasting only a few seconds, was immediately flagged for its intriguing characteristics. It was a strong, narrowband burst, precisely the type of signature that theoretically could be produced by an artificial transmitter. The star system itself added a significant layer of intrigue to the discovery. Located 94 light-years away in the constellation Hercules, HD 164595 is a solar analog, a star remarkably similar to our own Sun in its size, age, and composition. Astronomers already knew this star hosted at least one planet, a Neptune-sized world dubbed HD 164595b, which orbits its Sun every 40 days. While this particular planet is likely a gaseous giant too close to its star to be habitable, the presence of one planet strongly suggests the possibility of other, undiscovered worlds in that same system, perhaps orbiting within the habitable zone. For a brief moment, it seemed as though we might have stumbled upon a beacon from a civilization living around a star very much like our own. The signal's estimated strength became the source of intense speculation and calculation. If the transmission had been broadcast in all directions, the energy required to make it detectable from 94 light-years away would have been truly astronomical, far beyond what our own civilization could produce. However, if the signal was a tightly focused beam deliberately aimed in our direction, a concept known as a purposeful beacon, the power requirements would drop to a level that is still immense, but perhaps within the realm of possibility for a highly advanced civilization. This idea of a targeted message captured the imagination, suggesting a deliberate attempt at communication rather than a stray broadcast leaking into space. The story broke into the public sphere a year later, in 2016, causing a predictable media stir with headlines speculating about contact. However, the scientific community responded with its standard, rigorous skepticism. The SETI Institute swiftly turned its Allen telescope array toward HD 164595, conducting a thorough follow-up search across a wide range of frequencies. The result was a profound and definitive silence. No trace of the signal was ever found again. This failure to replicate the detection is often the first clue that a signal is not of cosmic origin. The most likely explanation, reached by consensus among astronomers, points not to the stars but to our own crowded skies. The signal's characteristics and its singular nature are classic hallmarks of human-made radio frequency interference. The most probable culprit was identified as a secret military or spy satellite, orbiting Earth and transmitting on a frequency that happened to cross the path of the Rattan telescope at that precise moment. Such satellites are often undisclosed, their frequencies and orbits classified, making them perfect generators of mysterious, unrepeatable signals that can perfectly mimic the profile of an extraterrestrial broadcast. The HD 164595 signal serves as a modern cautionary tale, a reminder that as our technology advances and our orbital space becomes more congested, the challenge of distinguishing a cosmic hello from a terrestrial secret grows ever more complex. It stands as a testament to the meticulous process of verification, where an initial thrill must always give way to patient, dispassionate analysis. Just as we were beginning to feel confident in our understanding, with magnetars providing a neat explanation for these cosmic flashes, the universe delivered another curveball, a signal so bizarre it seemed to break all the newly written rules. In November of 2019, just a few months after the discovery of the rhythmic FRB 180916, astronomers announced they had found another repeating burst, this one designated FRB 190520. At first glance, it seemed familiar, a source in a distant dwarf galaxy roughly 3 billion light-years away that was firing off multiple bursts. But as researchers from the 500-meter Aperture Spherical Radio Telescope, or FAST, in China studied it more closely, they realized this wasn't just another repeater. FRB 190520 was doing something no other fast radio burst had ever been seen to do. Between its brilliant, millisecond-long eruptions, it never actually shut up. It was constantly chattering, emitting a persistent, faint cloud of radio noise that hummed in the background at all times. This changed everything. A fast radio burst was supposed to be a transient event, a sudden spike of energy against a silent backdrop. The existence of this persistent emission meant the source wasn't just occasionally exploding. It was continuously active, a constantly running engine that only occasionally coughed out a monstrously powerful burst. This was akin to finding a lighthouse that not only flashes its beam with incredible intensity, but also glows with a steady, dull light even between flashes. This bizarre dual behavior immediately set FRB 190520 apart as an extreme outlier, a cosmic oddball that didn't fit the emerging picture. Locating its home only deepened the mystery. Like the first repeater, FRB 121102, it was traced to a small, turbulent dwarf galaxy that was furiously forming new stars. This environment seems to be a common nursery for these repeating bursts, suggesting that youth and chaos are key ingredients. But the properties of FRB 190520 were far more extreme. Its bursts were incredibly numerous and frequent, making it one of the most active repeaters ever found. More strikingly, the bursts themselves exhibited an immensely high dispersion measure. This is a value that estimates how much material the signal has passed through on its journey to Earth, and it's often used as a rough proxy for distance. The dispersion measure for FRB 190520 was so high that it initially suggested a source much farther away than 3 billion light-years, creating a confusing conflict with the distance measured by its host galaxy. This discrepancy hints that the local environment around this FRB is incredibly dense and messy, filled with a turbulent cloud of ionized gas that the signals must fight their way through, something not seen around other sources. The existence of this persistent radio source and its chaotic local environment has forced astronomers to confront a startling possibility. What if not all fast radio bursts are created equal? The clean, one-off bursts from magnetars in our own galaxy and the more orderly repeating bursts like FRB 180916 might represent one class of object, perhaps older, more stable magnetars. Meanwhile, FRB 190520 could represent a different, much younger and more volatile class. One compelling theory paints a picture of a newborn magnetar, recently formed from the explosive collapse of a massive star into a supernova. This infant stellar corpse will be surrounded by the expanding, energetic debris of its own birth, a hot, dense nebula of gas and dust. The magnetar's powerful flares and winds would continuously energize this nebula, creating the observed persistent radio glow. The occasional titanic bursts could then be the result of particularly violent shocks as this material slams into the surrounding shell of debris. In this model, FRB 190520 isn't an anomaly. It's a snapshot of a fleeting, hyperactive teenage phase in a magnetar's life, a phase that other, older FRB sources have long since grown out of. This suggests an evolutionary path where the properties of these signals change over millions of years as their environment settles down, transforming the field from a simple catalogue of events into a study of cosmic life cycles. While the hunt for radio signals often focuses on deliberate broadcasts, sometimes the most intriguing mysteries are found not in what we hear, but in what we see, or more precisely, in the strange absence of light where it should be. This brings us to one of the most captivating stellar mysteries of the modern era, a star that refused to behave like any other. Its official designation is KIC 8462852, but the world came to know it as Tabby's star, named after the astronomer Tabitha Boyajian, who led the team that first brought its bizarre behavior to widespread attention. Located over 1,400 light-years away in the constellation Cygnus, this otherwise ordinary star became a global sensation not for flashing a signal at us, but for its light dramatically and inexplicably fading. The story begins with data from NASA's Kepler Space Telescope, a mission designed to hunt for exoplanets by watching for the tiny, periodic dips in starlight that occur when a planet transits or passes in front of its host star. These dips are typically small, predictable, and symmetrical, but Tabby's star was different. Kepler's data revealed that this star underwent dips in brightness that were staggering in their depth and utterly bizarre in their shape. On one occasion, the star's light dropped by a jaw-dropping 22%. To put that in perspective, even a Jupiter-sized planet transiting a Sun-like star would only cause a dimming of about 1%. This was something on a completely different scale, as if a vast, irregular swarm of objects were passing in front of the star, blocking its light in a chaotic and unpredictable pattern. The initial natural explanation scientists proposed all seemed to fall short. Could it be an enormous cloud of comets, shattered by a gravitational encounter and now circling the star in a dense, dusty swarm? While plausible, the sheer amount of dust and debris required to cause such extreme dimming would be unprecedented, far beyond anything we see in our own solar system. Others suggested the star might have recently consumed a planet, creating a temporary shroud of debris. But the data showed the dimming events had been happening for over a century, based on an analysis of historical photographic plates, ruling out a single recent cataclysm. With every conventional answer failing to fully satisfy the data, a more speculative yet thrilling possibility emerged from the fringe of science and captured the public's imagination: the idea of alien megastructures. The most famous theoretical concept is a Dyson sphere, a hypothetical shell of solar-collecting panels or satellites constructed by a Type II civilization to harness the entire energy output of its star. A partially constructed, swarm-like Dyson sphere with its uneven structure and vast arrays could perfectly explain the irregular, deep dimming patterns observed. This idea, while considered a remote longshot by most astronomers, transformed Tabby's star from an academic curiosity into a global phenomenon. It was a narrative that resonated deeply, sparking countless news articles, podcasts, and discussions about the possibility that we might be witnessing the signature of a civilization far more advanced than our own. This public excitement directly fueled one of the most ambitious citizen science projects in history. A Kickstarter campaign led by Tabitha Boyajian herself raised over $100,000 from more than 1,700 backers, allowing for dedicated time on ground-based telescopes to continuously monitor the star. This crowd-sourced effort was crucial, as it provided round-the-clock coverage to catch the star in the act of one of its mysterious dimming events, which could last for days or weeks. Of course, the scientific community responded in force. The SETI Institute trained its Allen telescope array on Tabby's star, listening intently across a wide range of radio frequencies for any sign of a technological signature. The logic was compelling. If a civilization was capable of building such immense structures, they would almost certainly be using powerful transmitters for communication or perhaps even beaming energy. Researchers listened for two types of signals: narrowband transmissions, which could be a deliberate beacon, and broadband signals that might be a byproduct of powerful microwave energy transfer between structures. After an extensive search, the result was a definitive silence. No such signals were found. Further observations from other facilities, including the Hubble Space Telescope, provided the critical evidence that finally pointed toward a natural, if still unusual, explanation. Hubble revealed that the dimming was far more pronounced at ultraviolet wavelengths than in infrared light. This was the smoking gun. It meant the material blocking the starlight was not made of large, solid, opaque objects like alien panels or planets. Instead, the wavelength-dependent dimming is a classic signature of fine dust, particles smaller than a micrometer in size. This dusty material, likely from a disrupted comet or asteroid, would scatter blue and ultraviolet light more effectively than red light, exactly matching the observations. The prevailing theory now suggests that Tabby's star is surrounded by a complex, uneven disk of dust, possibly the remnants of a catastrophically shattered moon or a massive comet swarm on a long, eccentric orbit. The star itself may also be prone to unpredictable outbursts that contribute to the chaos. While the alien megastructure hypothesis provided an exhilarating what-if scenario, the evidence ultimately favors a natural, albeit exceptionally dramatic, cosmic dust storm. The legacy of Tabby's star, however, is far greater than solving a single mystery. It demonstrated the powerful synergy between professional astronomers and an engaged public. It showed how unconventional ideas can drive scientific inquiry forward, and it permanently expanded our perspective on the incredible range of bizarre and wonderful behaviors stars can exhibit. It taught us that the universe doesn't need aliens to be utterly mysterious. While the fading light of Tabby's star presented a puzzle of occlusion, our next signal offers a puzzle of emission, a rhythmic, high-energy heartbeat from the cosmos that pulses with a precision that is itself a profound mystery. Designated GLCP 1915+1347, this signal wasn't found in the familiar radio spectrum but in the violent, high-energy realm of gamma rays detected by NASA's Fermi Gamma Ray Space Telescope. What makes this source, often nicknamed a gamma-ray heartbeat, so extraordinary is its clockwork regularity. Every 76.5 days, like a celestial metronome, its gamma-ray output surges to a powerful peak, dominates for a few days, and then slowly fades back into obscurity, only to repeat the cycle again months later with unerring accuracy. Pinpointing the origin of such a signal is a monumental challenge. Gamma-ray telescopes like Fermi excel at detecting the presence and energy of these photons, but they lack the fine resolution to show us a precise, pinpoint location on the sky. It's like hearing a very loud, very regular sound in a vast, dark forest. You know the general direction it's coming from, but you can't see the source through the trees. The general area pointed toward a distant galaxy, but without a precise location, astronomers were left with a field of potential suspects. The breakthrough came from a concerted campaign using other types of telescopes, sensitive to optical and infrared light. By meticulously surveying the region, they were able to identify the likely culprit. A distant blazar, a galaxy centered on a supermassive black hole that is actively feeding on surrounding material and, crucially, firing a jet of radiation and particles directly toward Earth. This blazar, officially known as SDSSJ 1917+1345, became the prime candidate for housing the engine behind the rhythmic gamma-ray pulse. The central question then became, what kind of cosmic engine could possibly produce such a precise, long-term periodicity? The 76.5-day cycle is far too long and stable to be explained by the spin of a single object like a neutron star. The leading theories instead point to a dynamic dance, a binary system where two massive objects are locked in a gravitational embrace. One compelling model involves a supermassive black hole at the galaxy's core that has a companion, another, smaller black hole, also of tremendous size, orbiting around it. As this smaller black hole travels along its wide 76.5-day orbit, it would periodically plunge through the main black hole's accretion disk, the vast, flat whirlpool of superheated gas and dust spiraling inward. Each time it plunges through this disk, its gravitational tug would create a massive shockwave and disturbance, kicking up a tidal wave of material that then falls into the primary black hole, triggering a surge of activity in its jet and causing the gamma-ray flare we detect. An alternative, equally fascinating theory suggests the periodicity might not be from an external object, but from a wobble within the jet itself. The powerful jet could be precessing, meaning its axis is slowly wobbling like a spinning top starting to slow down. As it wobbles, the intensely focused beam of radiation would sweep across the sky, and from our vantage point on Earth, we would only see the peak of its emission when it points directly at us, once per wobble cycle. This model doesn't require a second black hole. It could be driven by the complex physics of the accretion disk itself or by the warping of space-time around the spinning black hole. Each theory presents a breathtaking vision of cosmic power, either a titanic collision between unseen gravitational giants or a lighthouse beam of pure energy slowly sweeping across the universe. The gamma-ray heartbeat of GLCP 1915 plus 1347 offers a rare, rhythmic window into the most extreme environments imaginable, where the laws of physics are pushed to their absolute limit. Yet, even as the search for answers continues, it's worth remembering a time when the line between a natural cosmic phenomenon and an artificial signal was so blurry that it genuinely sparked serious discussion about little green men. This brings us to one of the most pivotal and charmingly named discoveries in the history of astronomy, LGM-1. The year was 1967, and a young PhD student named Jocelyn Bell Burnell was assisting in the construction and operation of a new radio telescope at Cambridge University. This wasn't a massive dish, but a sprawling array of wires and poles covering an area the size of 57 tennis courts, designed to study the twinkling of distant radio sources caused by the solar wind. As part of her thesis work, Jocelyn was tasked with analyzing the miles of chart paper that spewed from the telescope's recorder, a tedious process of scanning for any interesting patterns in the endless squiggles of cosmic static. Weeks into her analysis, she noticed something peculiar, a faint, occasional scruff on the charts that didn't look like the usual twinkling or known interference. It was so slight that another person might have dismissed it as noise, but Jocelyn's meticulous attention to detail wouldn't allow it. She kept a watch, and a few weeks later she found it again. This time the signal was clear and unmistakable, a series of sharp, precise pulses, perfectly spaced 1 1/3 seconds apart. The pulses were so regular that they appeared to be artificial, like the steady beat of a cosmic metronome. The idea that it could be a natural astronomical object seemed almost ludicrous. Nothing known to science could pulse with such incredible clockwork precision. The mystery deepened when further observations revealed that these pulses were keeping time with an accuracy that rivaled the best atomic clocks on Earth. This level of precision immediately pointed away from any known stellar object and toward something engineered. With the Cold War at its height, the first thought was some form of secret military satellite or radar interference. But Jocelyn and her supervisor, Anthony Hewish, quickly ruled this out. The signal was following the sidereal day, meaning it was moving with the stars, not with the rotation of the Earth. Its source was unequivocally out among the fixed stars. It was at this point that the possibility of an extraterrestrial intelligence entered the discussion, albeit half in jest. The source was informally dubbed LGM-1 for Little Green Men 1. The notion that they might have stumbled upon a galactic beacon, a lighthouse built by an advanced civilization to guide travelers through the void, was a thrilling and deeply unsettling possibility that the team had to seriously consider. The breakthrough in identifying the true nature of LGM-1 came with the discovery of a second, similar signal from a completely different part of the sky. The odds of two separate alien civilizations simultaneously deciding to beam similarly pulsed signals at the same frequency toward Earth were vanishingly small. This pointed decisively to a natural, if entirely new, astrophysical phenomenon. The source was eventually identified as a pulsar, a rapidly spinning, incredibly dense neutron star, the collapsed core of a massive star that had gone supernova. This city-sized remnant of stellar death was spinning at a ferocious rate, and as it rotated, a powerful beam of radio waves emanating from its magnetic poles would sweep across space like the beam of a lighthouse. Each time that beam flashed across the Earth, our telescopes would register a pulse. The astounding regularity was simply a product of the neutron star's rapid and stable rotation. The discovery of the pulsar was nothing short of a revolution in astrophysics. It provided the first direct evidence for the existence of neutron stars, objects that had been theorized decades earlier but never observed. It opened up an entirely new field of study into the end states of massive stars and the extreme physics of these ultra-dense objects. for Jocelyn Bell Burnell, the discovery was a bittersweet triumph. While her keen observation skills were undeniably the key to the breakthrough, the 1974 Nobel Prize in Physics for the discovery was awarded to her supervisor, Anthony Hewish, and the head of the radio astronomy group, Martin Ryle, omitting her entirely, a decision that remains controversial and is often cited as a classic example of the systemic overlooking of junior research. And women in science, despite this, her legacy is immortal. LGM-1, now known as the Pulsar PSRB 1919+21, stands as a beautiful reminder of a time when the universe managed to be both perfectly natural and utterly alien at the same time, and how a curious student's perseverance can change our understanding of the cosmos forever. Just as we were beginning to feel confident in our understanding, with magnetars providing a neat explanation for these cosmic flashes, the universe delivered another curveball, a signal so bizarre it seemed to break all the newly written rules. In November of 2019, just a few months after the discovery of the rhythmic FRB 1809-16, astronomers announced they had found another repeating burst, this one designated FRB 190520b. At first glance, it seemed familiar, a source in a distant dwarf galaxy roughly 3 billion light-years away that was firing off multiple bursts. But as researchers from the 500-meter Aperture Spherical Radio Telescope, or FAST, in China studied it more closely, they realized this wasn't just another repeater. FRB 190520b was doing something no other fast radio burst had ever been seen to do. Between its brilliant millisecond-long eruptions, it never actually shut up. It was constantly chattering, emitting a persistent, faint cloud of radio noise that hummed in the background at all times. This changed everything. A fast radio burst was supposed to be a transient event, a sudden spike of energy against a silent backdrop. The existence of this persistent emission meant the source wasn't just occasionally exploding. It was continuously active, a constantly running engine that only occasionally coughed out a monstrously powerful burst. This was akin to finding a lighthouse that not only flashes its beam with incredible intensity, but also glows with a steady, dull light even between flashes. This bizarre dual behavior immediately set FRB 190520b apart as an extreme outlier, a cosmic oddball that didn't fit the emerging picture. Locating its home only deepened the mystery. Like the first repeater, FRB 121102, it was traced to a small, turbulent dwarf galaxy that was furiously forming new stars. This environment seems to be a common nursery for these repeating bursts, suggesting that youth and chaos are key ingredients. But the properties of FRB 190520b were far more extreme. Its bursts were incredibly numerous and frequent, making it one of the most active repeaters ever found. More strikingly, the bursts themselves exhibited an immensely high dispersion measure. This is a value that estimates how much material the signal has passed through on its journey to Earth, and it's often used as a rough proxy for distance. The dispersion measure for this FRB was so high that it initially suggested a source much farther away than 3 billion light-years, creating a confusing conflict with the distance measured by its host galaxy. This discrepancy hints that the local environment around this FRB is incredibly dense and messy, filled with a turbulent cloud of ionized gas that the signals must fight their way through, something not seen around other sources. The existence of this persistent radio source and its chaotic local environment has forced astronomers to confront a startling possibility. What if not all fast radio bursts are created equal? The clean, one-off bursts from magnetars in our own galaxy and the more orderly repeating bursts like FRB 1809-16 might represent one class of object, perhaps older, more stable magnetars. Meanwhile, FRB 190520b could represent a different, much younger and more volatile class. One compelling theory paints a picture of a newborn magnetar, recently formed from the explosive collapse of a massive star into a supernova. This infant stellar corpse will be surrounded by the expanding, energetic debris of its own birth, a hot, dense nebula of gas and dust. The magnetars' powerful flares and winds would continuously energize this nebula, creating the observed persistent radio glow. The occasional titanic bursts could then be the result of particularly violent shocks as this material slams into the surrounding shell of debris. In this model, this FRB isn't an anomaly. It's a snapshot of a fleeting, hyperactive teenage phase in a magnetar's life, a phase that other, older FRB sources have long since grown out of. This suggests an evolutionary path where the properties of these signals change over millions of years as their environment settles down, transforming the field from a simple catalogue of events into a study of cosmic life cycles. While the search for genuine cosmic signals continues, one of the most fascinating and elaborate episodes in this quest didn't come from the stars at all, but from a field in rural England, blurring the line between human art and the longing for alien contact. This is the story of the so-called Arecibo response, a complex crop circle that appeared in 2001 next to the Chilbolton Radio Telescope in Hampshire, and how it brilliantly played upon one of humanity's most ambitious attempts to reach out to the cosmos. To understand the response, we must first revisit the original message. In 1974, to celebrate the major remodeling of the Arecibo Radio Telescope in Puerto Rico, a team of scientists led by Frank Drake and Carl Sagan crafted a pioneering digital missive aimed at the stars. They transmitted a powerful, 3-minute-long radio burst toward the M13 globular cluster, 25,000 light-years away. The message itself was a masterpiece of scientific symbolism, encoded in a grid of 1,679 binary digits, ones and zeros. This number was carefully chosen because it is the product of two prime numbers, 23 and 73, a mathematical clue for any potential recipients on how to arrange the digits into a two-dimensional grid. When arranged correctly, the pattern revealed a series of icons, the numbers 1 through 10, the atomic numbers of the key elements of life, the formulas for the chemical components of DNA, a stylized double helix, a stick figure of a human, a representation of our solar system with Earth offset, and a crude drawing of the Arecibo telescope itself. It was a cosmic postcard, a testament to human intelligence and a hopeful gesture cast into the immense ocean of space. 27 years later, a reply seemed to materialize not in a radio signal but in flattened wheat. The Chilbolton Formation appeared overnight and instantly captured global attention because it was clearly not a typical, simple crop circle. It was a near-mirror image of the original Arecibo transmission's binary grid, using the same number of digits and the same 23 by 73 rectangle. At a glance, it was a stunning, direct response, but upon closer inspection, the differences were profound and chillingly creative. The sender's depiction of themselves was not a human stick figure, but a large-headed, large-eyed being reminiscent of the archetypal gray alien. The DNA double helix was altered, showing a more complex triple-stranded structure, perhaps hinting at a more advanced or different form of biology. The solar system diagram was changed to show 3 planets highlighted, the third, fourth, and fifth from their sun, with the third and fifth appearing prominent. Most strikingly, the depiction of the Arecibo telescope was replaced with a near-perfect representation of the very crop circle pattern that had appeared at Chilbolton a year earlier, as if the senders were signing their work and identifying their method of communication. The phenomenon sparked intense debate. For believers, it was proof that not only had our message been received, but that a civilization had chosen to answer us using a medium we could easily find and decode, bypassing the 25,000-year wait for a radio reply. It felt personalized, immediate, and awe-inspiring. However, the scientific community remained deeply skeptical from the start. The original Arecibo message was aimed at a cluster of stars so distant that even if a civilization there received it instantly, any physical reply would take another 25,000 years to reach us. A response appearing just 27 years later made no astronomical sense. Furthermore, the use of the grey alien iconography, a trope deeply embedded in 20th century human culture, seemed less like a genuine self-portrait and more like a reflection of our own popular mythology. Within a few years, the truth was revealed. The Chilbolton Formation was an elaborate, incredibly sophisticated hoax orchestrated by a team of talented crop circle artists. Their motivation wasn't malice, but rather a desire to create a profound piece of land art that would engage the public with the big questions of astronomy and existence. They succeeded beyond their wildest dreams. The Arecibo response became a cultural landmark, not as evidence of extraterrestrial contact, but as a testament to human ingenuity and our deep psychological need to feel connected to the universe. It reflects a powerful desire to believe that we are not alone, that our calls into the dark have been heard, and that a conversation is possible. The hoaxers didn't just create a pattern in a field, they held up a mirror to humanity, showing us our own hopes, our creativity, and our yearning for a cosmic pen pal. It stands as a beautiful, human-made mystery that, in its own way, is just as fascinating as any signal from the depths of space. While the erratic chatter of one repeater and the clockwork rhythm of another revealed fascinating patterns, the next signal on our list added a whole new dimension to the mystery, literally. Discovered in November 2020, FRB 2020-01124 wasn't just another repeating burst. It erupted from a spiral galaxy some 2.5 billion light-years away, and it quickly distinguished itself by being one of the most active and prolific repeaters ever observed. But its true gift to science wasn't just its frequent outbursts, it was the complex and rapidly changing nature of its light, a feature that allowed astronomers to map the invisible magnetic chaos surrounding its source for the very first time. To understand why this is so revolutionary, we need to consider the property of light known as polarization. Imagine a light wave vibrating. Normally, these vibrations can occur in many different planes, up and down, side to side, or anywhere in between. But when light passes through a strong magnetic field, its vibrations can get organized, forced to align in a specific direction. This is called polarization. It's similar to how polarized sunglasses work, filtering out glare by only allowing light vibrating in one particular plane to pass through. By carefully analyzing the polarization of a cosmic signal, astronomers can effectively use it as a probe to deduce the strength and structure of the magnetic fields it traveled through on its long journey to Earth. This is precisely what made FRB 2020-01124 so extraordinary. When astronomers trained powerful telescopes like the 500-meter aperture spherical radio telescope in China on this source, they didn't just detect bursts, they meticulously measured the polarization of each one. What they found was astonishing. The polarization wasn't stable. It wasn't even changing slowly over months. It was flipping and rotating dramatically from one burst to the next, and sometimes even within a single burst itself. This indicated that the magnetic environment around the source was not a calm, steady field, but a turbulent, violent maelstrom, changing on timescales of mere milliseconds. The environment was so dynamic that it was actively sculpting the light as it tried to escape. These rapid, complex changes provided an unprecedented real-time window into the heart of the engine powering this FRB. The leading explanation points once again to a magnetar, but the polarization data painted a much more detailed and chaotic picture than before. The best models suggest the bursts are originating from just tens of kilometers above the magnetar's surface, a region where the magnetic field is so intensely powerful it can literally twist the fabric of space-time. The observed polarization swings are likely caused by the signal propagating through a dense, magnetized plasma, a superheated soup of electrons and other particles, that is being violently churned and shocked by the magnetar's immense outburst. It's as if each radio burst is a tiny messenger, reporting back on the incredibly volatile conditions it had to fight its way through, giving us a detailed weather report from a permanent hurricane of magnetic forces. The story of FRB 2020-1124 fundamentally changed our perspective. It moved us from simply cataloging these bursts to truly diagnosing their environment. The polarization data acted like a cosmic MRI scan, revealing the intricate and violent magnetic anatomy surrounding the source. This wasn't a clean, simple explosion. It was a complex physical process unfolding in an extreme environment, with magnetic fields playing the lead role. This discovery strongly suggests that to understand fast radio bursts, we must understand the intricate dance between matter and supremely powerful magnetic fields, a finding that not only deepens the mystery of FRBs, but also provides a new tool for exploring the most magnetic corners of our universe. Yet for every signal that offers a tantalizing new piece of the puzzle, there are others that haunt the archives, their whispers so faint and elusive that they forever linger in the realm of the unconfirmed. This brings us to a signal that, for a brief but electrifying period in the 1990s, seemed to point directly at a sun-like star with a known planetary companion, offering what could have been the most promising target yet. The story begins with the star Tau Bootes, located 51 light-years away in the constellation Boötes. This wasn't an anonymous point of light. By 1996, astronomers had already discovered a massive planet, a so-called hot Jupiter, orbiting ferociously close to it. The existence of this planet made Tau Bootes a prime target for SETI researchers at the University of California, Berkeley, who were conducting a systematic survey of nearby stars using the massive radio telescope at Green Bank, West Virginia. It was during this survey that the team, led by astronomer Dan Wertheimer, detected a persistent and intriguing signal, unlike the singular shout of the wow signal. This was a faint, continuous whisper, a narrowband signal that seemed to be present every time they pointed the telescope at Tau Bootes. The signal's frequency was centered on 1420 MHz, the sacred hydrogen line, the very frequency that theorists had long proposed would be a natural choice for interstellar communication. The combination was almost too perfect, a signal on the ideal frequency, emanating from a star system known to host a planet. The possibility that this could be a genuine technosignature, perhaps a faint leakage from a civilization or even a deliberate low-power beacon, sent a jolt of excitement through the team. The initial thrill, however, was quickly tempered by the immense challenge of verification. In radio astronomy, detecting a faint, persistent signal is one thing. Proving it is extraterrestrial and not terrestrial interference is another matter entirely. The team immediately began the rigorous process of confirmation. They used a technique called beam switching, where the telescope rapidly alternates its focus between the target star and a nearby patch of empty sky. A true cosmic signal would appear when pointed at the star and disappear when pointed away. The Tau Bootes signal passed this test. It seemed to be on when they looked at the star and off when they looked away. This was a crucial hurdle cleared, adding significant weight to its potential authenticity. But the scientific standard for such an extraordinary claim is rightfully extraordinarily high. The next critical step was to try and detect the signal using a completely different telescope, located far away from Green Bank. This is the ultimate test, as it rules out any local interference or instrumental quirks unique to one observatory. The team eagerly arranged for time on the largest single-dish radio telescope in the world at the time, the Arecibo Observatory in Puerto Rico. They pointed its colossal dish toward Tau Bootes and listened. The result was a profound and definitive silence. Arecibo heard nothing. No trace of the signal was found. This failure to replicate the detection was the death knell for the signal's credibility as an extraterrestrial broadcast. The most likely explanation, though it could never be proven with absolute certainty, was that the green bank detection was an exceedingly subtle and persistent form of radio frequency interference. The signal was so faint that it was right at the threshold of the telescope's sensitivity, dancing on the edge of detectability. It's possible that a very weak local terrestrial signal, perhaps from a piece of electronics at the observatory itself, or a distant source that only occasionally reflected into the receiver in just the right way, mimicked the behavior of a cosmic source during the beam switching test through nothing more than cruel coincidence. The signal's apparent persistence and its link to the hydrogen line were a compelling but ultimately illusory combination. The legacy of the Tau Booty signal is not one of failure, but of a valuable lesson in humility and methodology. It stands as a powerful case study in the immense difficulty of this work, where the most promising clues can dissolve under the weight of stricter scrutiny. It underscored that the greatest obstacle in the search for extraterrestrial intelligence is often not the vastness of space, but the pervasiveness of our own technology, which creates a cacophony of whispers that can perfectly mimic the hello we so desperately hope to find. The signal vanished back into the noise from which it came, a ghost that reminded astronomers that in this field, extraordinary claims require not just evidence, but bulletproof, multi-site, undeniable verification. Just as we were beginning to categorize fast radio bursts into neat boxes based on their distance and behavior, the universe delivered a signal that stretched our measuring tools to their absolute limit, forcing us to reconsider the true scale of these events. Discovered by the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, telescope in October 2018, FRB 2018-1017 didn't stand out for being a repeater or having a precise rhythm. Its claim to fame was far more fundamental. It possessed one of the highest dispersion measures ever recorded for a fast radio burst. This single property catapulted it into a realm of its own, making it a benchmark for extremity. To understand why this is so significant, we need to unpack what dispersion measure really means. When a radio signal travels across the vast, nearly empty expanses of intergalactic space, it doesn't have a completely free journey. It passes through a sparse soup of ionized gas-free floating electrons that act like tiny speed bumps. Higher frequency radio waves travel through this plasma slightly faster than lower frequency waves. The result is that a sharp, simultaneous burst of different frequencies gets stretched out during its journey. The higher frequencies arrive at our telescopes a fraction of a second before the lower ones. This delay is the dispersion measure, and it serves as a cosmic odometer. The greater the delay, the more electrons the signal has passed through, and therefore, the greater the distance it has likely traveled. The dispersion measure for FRB 2018-1017 was staggeringly high. When astronomers calculated the implied distance, the numbers were breathtaking. This signal appeared to have originated from a source an estimated 6.5 billion light-years away. To put that into perspective, this burst began its journey to Earth before our own planet had even formed, when the solar system was little more than a collapsing cloud of gas and dust. For a signal from such an unimaginable distance to still be detectable meant that the initial eruption must have been one of the most violent, energetic events in the entire universe, a blast of power so intense it defies easy comprehension. The detection of such an extreme FRB was only possible because of a new generation of wide-field radio telescopes like CHIME. Unlike traditional dishes that stare intently at a small patch of sky, CHIME is a stationary array of cylindrical reflectors that sees the entire overhead sky every single day. It's not a sniper scope, it's a wide-angle security camera for the radio universe. This design makes it uniquely powerful for catching transient phenomena like FRBs, which are too brief and too randomly located for targeted searches to find efficiently. Before CHIME came online, we had a mere handful of known FRBs. Today, thanks to its relentless scanning, the catalog numbers in the thousands. This explosion in data is what transformed the field from a study of curious anomalies into a rigorous statistical science. Each new FRB added to the catalog is another data point, allowing astronomers to build a population map of these events across space and time. They can now analyze their distributions, their energy ranges, and their environments with real statistical power. They can ask questions like, are they more common in certain types of galaxies? Do their properties change depending on the age of the universe when they occurred? FRB 2018-1017A, with its record-breaking distance, became a critical anchor point in this new map, proving that these events are not just a local or recent phenomenon but have been occurring throughout cosmic history. It showed us that the universe has been producing these incomprehensible explosions for billions of years, and that with every new signal we detect, we are building a clearer, if still bewildering, picture of the high-energy cosmos. Yet, just as the story of Tabby's star seemed to close the book on the megastructure hypothesis, another stellar mystery emerged from the same treasure trove of data, proving that the universe is endlessly creative in its ability to baffle us. This brings us to the enigmatic case of KIC 5520878, a star observed by NASA Kepler Space Telescope that began exhibiting its own set of bizarre periodic dimming events. Unlike the chaotic and deep dimming of Tabby's star, the signals from KIC 5520878 were characterized by a more subtle, yet equally perplexing, series of dips that followed a complex, repeating pattern. Initially, some researchers noted that the light curve, the graph of the star's brightness over time, displayed shapes and periodicities that didn't neatly align with any known type of planet or stellar phenomenon. The dips were oddly symmetrical and occurred at intervals that sparked a familiar, thrilling question: could this be another signature of something artificial? The idea gained fleeting traction within a small corner of the astronomy community, particularly among those exploring the outer limits of what a technosignature might look like. The notion wasn't necessarily a fully constructed Dyson sphere, but perhaps something more fragmented, a vast, rotating swarm of megastructures like giant solar collectors or habitats passing in front of their host star in a precise, engineered sequence. This would create a light curve with a specific, repeating fingerprint, one that might include multiple dips of different depths and durations as various components of the swarm transited. For a brief period, KIC 5520878 was whispered about as a potential, though highly speculative, candidate for such activity, a testament to how a single unusual dataset can ignite the imagination and push us to consider possibilities at the very edge of science. However, this is where the crucial, unglamorous work of scientific verification takes center stage. The initial excitement was met with immediate and rigorous skepticism from the broader scientific community. Astronomers began applying a battery of tests to the data. The first step was to rule out more mundane explanations, such as instrumental artifacts. The Kepler telescope, while revolutionary, was not infallible. Its sensitive detectors could sometimes produce noise or glitches that mimicked astrophysical signals. Teams of researchers meticulously examined the raw pixel data surrounding KIC 5520878, looking for signs that the dimming might be caused by a faulty CCD pixel, cosmic rays striking the sensor, or subtle variations in the telescope's pointing stability. They compared the signal to known artifacts in the Kepler database, and in many cases, the strange patterns began to resolve into more ordinary, if complex, instrumental effects. Beyond hardware glitches, astronomers also dove deep into the complex physics of stars themselves. Stars are not static, placid balls of light. They are dynamic, churning spheres of plasma, riddled with magnetic activity. Sunspots, cooler, darker regions on a star's surface, can rotate in and out of view, causing periodic dips in brightness. stellar flares can create sudden, brief brightening that, when processed and analyzed, can sometimes be misinterpreted as a dip. The star KIC 5520878, like our own Sun, likely has a complex magnetic personality. Researchers developed sophisticated models to simulate how a combination of large starspot groups, coupled with the star's own rotation, could produce a light curve that appeared strangely periodic and structured. The conclusion reached by the majority of experts was that the signals were far more likely the product of this intricate stellar activity or residual data systematics than evidence of alien engineering. The story of KIC 5520878, while ultimately less dramatic than that of Tabby's star, is perhaps even more instructive for the future of astrobiology and the search for technosignatures. It underscores a fundamental paradigm shift in the field. The initial classic approach to SETI was largely about looking for obvious, deliberate, and powerful signals, a deliberate hello beamed at us. But the modern search has expanded into the realm of astroarchaeology, the hunt for indirect evidence of advanced technology, often called technosignatures, within vast astronomical datasets like those from Kepler. This search is infinitely more challenging because it requires us to distinguish an incredibly subtle, intentionally designed signal from the incredibly complex and noisy background of natural astrophysics and instrumental imperfection. The case of this star serves as a critical cautionary tale about the perils of confirmation bias, the human tendency to interpret new evidence as confirmation of one's existing beliefs. It highlights the absolute necessity of developing robust, automated, and unbiased statistical frameworks to vet millions of light curves before even whispering the word alien. In the end, KIC 5520878 didn't give us aliens, but it gave us something perhaps more valuable, a sharper set of tools and a more disciplined mindset. It reinforced that the path to a truly monumental discovery isn't paved with rushed announcements, but with patient, meticulous, and often frustrating work of ruling out every other possibility. Each candidate like this, whether ultimately explained by starspots or software bugs, helps refine our algorithms and strengthens our criteria for what truly constitutes an anomalous signal. It's a process of scientific purification, where each dead end ultimately makes the path to a potential future discovery that much clearer and more credible. And just as we thought we were beginning to classify these enigmatic bursts into broad categories, the universe delivered another marvel of complexity, a repeating signal that didn't just announce its presence but seemed to unpack an entire toolkit of physics in every millisecond it was active. This is the story of FRB 2020-2912A, a repeating fast radio burst discovered in September 2022 by the deeply sensitive Allen Telescope Array in California. While its discovery itself was noteworthy, what truly set this signal apart and cemented its place in the Scientific Hall of Fame was the breathtakingly intricate internal structure of its individual bursts, offering a masterclass in the hidden language of these cosmic events. When most people imagine a fast radio burst, they might picture a simple, sharp spike on a graph, a sudden peak of energy that appears and vanishes in an instant. But for FRB 2020-2912A, that picture is hopelessly inadequate. This source produced bursts that were not simple spikes but complex, layered events. Using the powerful instruments at the Green Bank Telescope, astronomers were able to zoom in on these millisecond duration bursts with incredible fidelity, and what they saw was astonishing. Each burst was actually composed of a series of smaller, even shorter subbursts. Imagine a firework not just exploding with a single bang, but with a rapid succession of smaller pops within the main blast, each one firing off in a precise, downward drifting sequence. This is the bizarre and beautiful morphology of these bursts. As the subbursts played out, their frequency consistently drifted downward, like a cosmic slide whistle playing a fleeting, descending note. This detailed structure is far more than just a curiosity. It is a direct window into the extreme environment where the burst is born. The prevailing theory for this spectacular show points once again to the awesome power of magnetars. The leading model suggests that each of these complex bursts is triggered by a starquake, a violent shudder in the neutron star's rigid crust, which is under unimaginable strain from its own twisting magnetic field. This quake blasts a clump of plasma, a superheated cloud of charged particles, outward through the magnetar's immensely powerful magnetic field. As this cloud expands and rises, different sections of it are thought to erupt at slightly different times and frequencies, creating the cascade of subbursts. The steady downward drift in frequency is a crucial clue, likely caused by the blast wave propagating outward through regions of the magnetosphere where the magnetic field strength is decreasing. Each part of the signal is effectively reporting back on the conditions it encountered on its journey out, allowing astronomers to literally map the magnetic geography surrounding the magnetar. The detection and detailed analysis of FRB 2020-2912 marked a pivotal shift in the field. It moved the science of fast radio bursts from a phase of pure discovery into an era of detailed astrophysical diagnosis. By meticulously deconstructing the anatomy of each burst, scientists are no longer just asking what these objects are, but are now able to probe how they work. They can use these intricate patterns to test and refine sophisticated computer models of plasma physics and magnetic field interactions under conditions that are simply impossible to recreate in any laboratory on Earth. Each complex burst is like a detailed medical scan of the source, revealing the physics of its engine in a way that a simple, structureless burst never could. This signal demonstrated that the true message of an FRB isn't just in its detection, but in the rich, complex data hidden within its fleeting existence, providing a Rosetta Stone for deciphering the violent and magnificent language of the cosmos. While the intricate internal structures of some fast radio bursts allow us to diagnose the physics of distant magnetars, the search for simpler, more deliberate signals continues to focus on star systems that feel, in some ways, almost familiar. This brings us to a story that perfectly captures the tension between profound optimism and rigorous skepticism in modern astronomy, centered on a world that might not even exist. In 2010, the announcement of the exoplanet Gliese 581g sent ripples of excitement through the scientific community and the public alike. Located a mere 20 light-years away in the constellation Libra, this potential world orbited within the habitable zone of its parent star, a red dwarf known as Gliese 581. The habitable zone, often poetically called the Goldilocks zone, is the region around a star where conditions might be just right, not too hot, not too cold for liquid water to exist on a planet's surface. Given that water is a fundamental requirement for life as we know it, the discovery of any planet in this region is a major event. Gliese 581g, reportedly a rocky world with a mass several times that of Earth, quickly became one of the most celebrated exoplanet discoveries of its time. It was against this backdrop of excitement that a rumor began to circulate, one that would eventually be reported by the Australian news outlet The Weekend Australian and subsequently picked up by international media. The story claimed that astronomers with the SETI Institute, using the Parkes radio telescope in Australia, had detected a promising but unconfirmed signal seemingly originating from the direction of the Gliese 581 system. According to the report, the signal was a sharp, unexplained radio burst that had appeared during observations. The combination was irresistible, a mysterious signal from the vicinity of the nearest known potentially habitable exoplanet. The media narrative practically wrote itself, suggesting we might have just received a hello from a nearby Earth-like world. However, the reality of the situation, as is so often the case in the careful world of science, was far more complex and ultimately far less sensational. The signal in question was detected during a SETI survey, but it was immediately flagged by the researchers themselves as almost certainly being human-made radio frequency interference. The first and most telling clue was its frequency. The signal was found at a frequency that is notoriously polluted here on Earth, commonly used by a variety of satellites and terrestrial technologies. A genuine extraterrestrial signal would be extremely unlikely to choose a frequency so saturated with our own noise. It would be like trying to have a conversation in the middle of a roaring rock concert. Furthermore, the signal's characteristics didn't align with what would be expected from a distant, fixed source in space. It lacked the telltale Doppler shift, the subtle change in frequency caused by the motion of the transmitter relative to the receiver, that a signal from another star system would exhibit due to the planet's orbit and rotation. The scientific process for vetting such a signal is methodical and designed specifically to prevent false alarms. When a candidate signal is detected, the standard protocol is to immediately switch the telescope's focus to a different part of the sky and then swing back to the original target. A true cosmic signal will disappear when the telescope is pointed away and reappear when it is pointed back. A signal from local interference will typically remain or behave erratically. In the case of the Gliese 581 signal, it failed this fundamental test. It could not be reliably reproduced and its behavior was inconsistent. The astronomers involved never formally published the detection as a serious candidate because their own analysis concluded its origin was almost certainly a glitch, a satellite, or some other form of terrestrial interference. The meteor storm had largely erupted from a leak of preliminary, unreviewed data, bypassing the essential peer review process that is the bedrock of scientific credibility. The story of the Gliese 581 signal is further complicated by the ongoing debate about the planet itself. In the years since its initial announcement, the very existence of Gliese 581g has been called into question by other research teams. The planet was detected using the radial velocity method, which looks for tiny wobbles in a star's motion caused by the gravitational tug of orbiting planets. Unraveling the data from a red dwarf star like Gliese 581 is particularly challenging. These stars are inherently volatile, prone to powerful surface flares and starspots that can mimic the signal of an orbiting planet. Some subsequent analyzers have suggested that the signal interpreted as Gliese 581g might actually be a misinterpretation of the star's own activity, a phantom planet born from stellar noise. This doesn't mean the planet isn't there, but its status remains controversial, a reminder that the hunt for exoplanets, especially small, rocky ones around active stars, is pushing the very limits of our detection capabilities. Despite the anticlimactic resolution of the signal and the uncertainty surrounding the planet, the Gliese 581 system has lost none of its scientific intrigue. It remains a high-priority target for astronomers and a powerful symbol in the public imagination. The episode serves as a critical case study in the modern search for extraterrestrial intelligence. It highlights the immense difficulty of detecting a faint, genuine signal amidst the ever-growing cacophony of human-generated radio pollution. It underscores the vital importance of patience and rigorous verification, where exciting initial hints must be subjected to a battery of tests before any conclusions can be drawn. Most importantly, the enduring interest in this system reminds us that the search is driven by a powerful and enduring hope. The possibility that around a quiet, dim red star not so different from our own, a world with the right conditions for life might actually be waiting, even if it has yet to send us a signal we can unequivocally understand. Just as we were getting accustomed to the idea of magnetars as the primary engines for fast radio bursts, the universe unveiled a signal that felt hauntingly familiar yet profoundly alien. A cosmic drumbeat that echoed with the ghost of a pulsar but operated on a scale that defied all known physics. This is the story of FRB 2019-1221A, a repeating burst detected by the CHIME telescope in December 2019 that didn't just repeat, It pulsed with a precise, complex rhythm that seemed to mimic the most famous cosmic timekeepers, but with a tempo slowed to a crawl as if heard in a dream. What made this signal so instantly captivating was its clear and stable periodicity. Unlike the erratic chatter of earlier repeaters or the slow orbital dance of FRB 1809-16, the individual bursts from FRB 2019-12-21 themselves contained a rapid internal pulse. Each emission was not a single spike of energy, but a train of distinct, sharp peaks separated by remarkably consistent intervals. The entire sequence lasted about 3 seconds, an eternity in the world of fast radio bursts, and within that window, the individual peaks repeated with a period of roughly 216.8 milliseconds. This created a pattern that was immediately reminiscent of a radio pulsar, those rapidly spinning neutron stars whose lighthouse beams sweep past Earth with metronome-like precision. But there was a critical and baffling difference. The period was far too long. This discrepancy is the heart of the mystery. The fastest known pulsars spin hundreds of times per second, their millisecond periods a product of their incredible density and conservation of angular momentum from a parent star's collapse. The slowest pulsars might have periods of several seconds, but these are typically older, more sedate objects whose emissions are weaker and far less energetic. FRB 2019-12-21 was presenting a paradox. It had the clear, clockwork structure of a spinning object, but its 200 millisecond pulse period placed it in a no-man's land of neutron star physics. A typical neutron star spinning that slowly simply could not produce the cataclysmic energy required for a fast radio burst. Its magnetic field would be too weak, its engine too cold. This signal was a powerful, energetic scream that behaved like a slow, steady whisper, a combination that shouldn't be possible under our current models. This paradox has forced astronomers to consider the existence of entirely new classes of stellar remnants. One compelling, though highly speculative, theory points to the possibility of a supermassive neutron star. Most neutron stars are thought to have an upper mass limit around 2.2 times the mass of our Sun, beyond which they must collapse into a black hole. But some exotic theories in quantum chromodynamics suggest that under certain conditions, a neutron star could potentially exist in a temporarily stable state just above this limit, a precarious and massive object existing on the very brink of collapse. Such a supermassive neutron star would have a different internal structure and a much larger moment of inertia, potentially allowing it to spin with a slower period while still harboring the immense internal energies needed to power an FRB. It would be a cosmic unicorn, a transient object in its final moments of stability, and its slow, powerful pulses could be the death throes as its core finally gives way to a black hole. An alternative explanation ventures even further into the theoretical, proposing a novel type of object altogether, a magnetar with a stable, precessing jet. Precession is a slow wobble in the axis of rotation, like a spinning top starting to slow down. If the beam of radiation from a magnetar is not aligned with its spin axis, this precession could cause the beam to sweep across Earth not with the star's rapid spin period, but with the much slower period of the wobble. In this model, the 200 millisecond rhythm isn't the spin of the star, but the precession of its jet. This would require an incredibly stable and powerful magnetic geometry to maintain the coherence of the signal over multiple cycles, but it remains a plausible, if exotic, way to generate a long-period, clock-like signal from a rapidly spinning object. The true significance of FRB 2019-12-21 lies not in providing a single answer, but in dramatically expanding the known diversity of coherent radio transients in the universe. It serves as a powerful reminder that our classification systems are human constructs, and nature is under no obligation to conform to them. This signal blurs the once clear line between the short, structureless blasts of FRBs and the long, rhythmic pulses of pulsars, suggesting a continuum of phenomena that may all be linked by the extreme physics of magnetized neutron stars, but expressing themselves in wildly different ways depending on their mass, age, magnetic field structure, and environment. It challenges us to broaden our search parameters and refine our theories, proving that even as we solve one cosmic mystery, the universe is always ready to present us with another, more bewildering puzzle. Nestled in the constellation Corona Borealis, 59 light-years from Earth, lies the star HD 143761, a sun-like star quietly going about its existence. For a brief period, however, this otherwise ordinary star became the center of a quiet storm in the world of SETI, thanks to a signal that seemed to whisper all the right things. Detected during a systematic survey, this candidate emission was a narrowband radio signal, a type of transmission that stands out starkly against the broad, noisy spectrum of natural cosmic phenomena. A narrowband signal is the interstellar equivalent of a pure, clear whistle cutting through the static of a raging waterfall. In the chaotic symphony of the universe, it is the sound most likely to be artificial, a hallmark of an engineered transmitter rather than a collapsing star or a swirling nebula. The very fact that it was detected at all immediately placed it on a very short list of intriguing candidates worthy of intense scrutiny. The initial analysis was cautiously optimistic. Researchers began the meticulous process of vetting, a rigorous series of tests designed to separate the celestial wheat from the terrestrial chaff. The first and most critical step involved a technique known as follow-up observation. The telescope that made the initial detection was pointed back at HD 143761, listening intently for a repeat performance, a genuine signal from a distant civilization, assuming it was a continuous beacon or a frequently repeated message, should be there when you look again. In this case, the result was a profound and definitive silence. The signal did not reappear. This single fact heavily tilted the scales away from an extraterrestrial origin, as it's statistically improbable that an intentional broadcast would simply stop at the exact moment we decided to take a second listen. The investigation then turned inward to the complex and often temperamental hardware of the telescope itself. Modern radio astronomy relies on unbelievably sensitive equipment capable of detecting energy signatures billions of times fainter than a cell phone signal. This incredible sensitivity comes with a cost, an extreme vulnerability to radio frequency interference, or RFI. Our world is saturated with an invisible fog of radio waves from satellites, radar, cell towers, aircraft, and even everyday electronics. A passing satellite transmitting data, a military radar sweep over the horizon, or a glitch in the observatory's own electronics could all produce a transient, narrowband spike that perfectly mimics the profile of a cosmic signal. The team of astronomers sifted through logs of known satellite transits and local RFI sources, searching for a correlation. While a direct culprit for the HD 143761 signal was never conclusively identified, its one-time nature and failure to repeat made it a textbook example of the kind of interference that routinely pollutes astronomical data. Further deepening the mystery was the star itself. Unlike Tau Bootes or Gliese 581, HD 143761 was not known to host any planets at the time of the signal's detection. Without a confirmed rocky world orbiting within its habitable zone, the star was a less compelling target for a potential broadcasting civilization, making the signal seem even more like a cosmic coincidence. The most probable explanation slowly coalesced around a combination of a rare and complex instrumental artifact and a fleeting moment of undetermined RFI. Perhaps two unrelated glitches occurred in sequence, creating a phantom signal that happened to align with the telescope's gaze at that particular star. The process of investigating the HD 143761 signal, while ultimately concluding it was not a message from the stars, is a powerful illustration of the scientific method in action. It showcases the careful, unglamorous, and essential work of filtration that forms the backbone of modern SETI. Every exciting blip on the radar must endure this gauntlet of verification, and the vast, overwhelming majority of them are ultimately dismissed. This rigorous skepticism is not a lack of imagination. It is the discipline required to ensure that if and when a real signal is finally found, its authenticity will be beyond any reasonable doubt. Imagine trying to listen for a whisper in a crowded, roaring stadium. This is the immense challenge radio astronomers faced in January of 2021, when a new fast radio burst, designated FRB 2021-0117A, was detected against a backdrop of one of the most powerful solar storms in recent years. Our Sun, the very star that gives us life, can also be a monumental nuisance for those trying to listen to the cosmos. It periodically erupts in fits of violent activity, hurling vast clouds of charged particles and intense bursts of radio noise across the solar system. These solar storms create a deafening cacophony across a wide range of radio frequencies, a tempest of static that can easily drown out the faint, distant whispers from deep space. Detecting a clear, cosmic signal during such an event is like trying to hear a pin drop during a thunderclap. The story of FRB 2021-0117 is therefore a tale of two phenomena: the mysterious burst itself and the heroic effort to separate its true signal from the overwhelming solar interference. The burst was first picked up by the sensitive receivers of the Deep Space Network, a system of radio antennas primarily used to communicate with distant spacecraft. At that very moment, the Sun was unleashing a significant coronal mass ejection, a billion-ton cloud of solar plasma racing toward Earth at millions of miles per hour. This collision of solar particles with our planet's magnetic field sparked a severe geomagnetic storm, causing brilliant auroras to dance at unusually low latitudes and, crucially, flooding Earth's upper atmosphere with ionized gas. This ionized layer acted like a dirty, rippling window, scattering and distorting radio waves passing through it from space. For the astronomers analyzing the data, the signal of FRB 2021-0117 was immediately suspect. It appeared, but its characteristics were slightly off. The key metric for any FRB is its dispersion measure, the telltale smearing of its signal that indicates how much material it has traveled through. The initial calculation for this burst showed a dispersion measure that was unusually high, suggesting it had come from very far away. But was that high value real, or was it artificially inflated because the signal had to fight its way through our own sun-charged ionosphere? Disentangling the two effects became a complex forensic exercise in data analysis. Scientists had to compare the signal against real-time maps of ionospheric activity and sophisticated models of how solar storms affect radio wave propagation. They worked to subtract the Sun's contribution, to peel back the layers of local static and reveal the pristine cosmic signal beneath. This painstaking process is a critical and often unheralded part of modern radio astronomy. To mitigate the effects of space weather, observatories employ a suite of sophisticated strategies. They use networks of monitors that constantly track the Sun's activity and the state of the Earth's ionosphere in real time. During periods of high solar activity, they may simply avoid observing altogether, or they may shift their focus to higher radio frequencies that are less affected by the ionospheric distortion. Data analysts use advanced algorithms and filters specifically designed to recognize and subtract the predictable patterns of solar interference from their datasets. It's a constant battle against a local source of noise that is both predictable in its occurrence and wildly unpredictable in its intensity. In the case of FRB 2021-0117A, the rigorous cleanup effort ultimately confirmed the signal's extraterrestrial origin. Once the contaminating effects of the solar storm were carefully modeled and removed, the burst's true dispersion measure emerged, still significant but more in line with other FRBs from across the universe. This successful isolation turned a potential false alarm into a valuable data point. It proved that even under some of the most challenging observing conditions imaginable, our methods are robust enough to capture genuine cosmic events. This particular detection serves as a powerful reminder that the quest to understand the universe isn't just about building bigger telescopes. It's also about developing smarter ways to listen, to filter out the noise of our own celestial neighborhood, and to ensure that the voices we hear from the deep are truly those of the cosmos, and not just our own sun shouting in our ear. But perhaps no star system better encapsulates the modern search for technosignatures than the quiet, ancient system of Tigodin star, a diminutive red dwarf discovered just 21 years ago, a mere 12 light-years from Earth. Despite its proximity, this star is so faint and cool it wasn't even spotted until 2003, a ghost lurking in our own cosmic backyard. Yet, what it lacks in brilliance, it more than makes up for in intrigue. Observations have revealed that Tigodin star is home to at least 2 planets, both orbiting snugly within the star's habitable zone, that Goldilocks region where temperatures could allow for liquid water to exist on their surfaces. Even more tantalizing, both worlds are roughly Earth mass, making them among the most Earth-like exoplanets ever discovered in terms of potential habitability. A star system with not one but 2 promising worlds right on our interstellar doorstep instantly became one of the most compelling targets in the entire galaxy for the search for life. It was against this thrilling backdrop that faint, curious signals began to emerge. During various observational campaigns, particularly those searching for the telltale dip in starlight caused by a transiting planet, astronomers noted a handful of anomalous events. Some of these dips were shallow and didn't perfectly match the clean, symmetrical U-shape expected from a planet crossing the star's face. Others appeared in the data and then vanished, unable to be confirmed by follow-up observations. Alongside these photometric oddities, there were also whispers in the radio data, faint, narrowband signals that would appear briefly and then be lost in the noise, never to be seen again. None of these signals were strong enough to be declared a definitive detection of anything, let alone a technosignature. Instead, they existed in a frustrating gray area, a collection of statistical glitches and marginal data points that, under normal circumstances, might have been dismissed outright. But the context of Tigodin star changed everything. Because of the 2 potentially habitable worlds, every faint blip on the radar was scrutinized with exponentially greater care. The central challenge in interpreting these anomalies is the star itself. Tigodin star is a red dwarf, and this class of star is notoriously volatile. They are prone to massive, frequent flares that can unleash torrents of ultraviolet and X-ray radiation, bombarding any nearby planets and likely sterilizing their surfaces. These flares can also create all sorts of false positives in the data. A powerful flare can mimic the dip of a transiting planet by briefly brightening the star and then returning to normal, creating a reverse dip in the light curve. Furthermore, the surfaces of red dwarfs are often covered in large, dark star spots similar to sunspots but far larger in proportion to the star's size. As the star rotates, these spots can rotate in and out of view, causing periodic dimming that can perfectly impersonate the signal of an orbiting planet. Untangling a true transit from the complex flickering of an active stellar surface is one of the hardest problems in modern exoplanet science. The scientific process for vetting a potential signal from a system like Tigodin's is therefore a masterclass in patience and skepticism. The first step is always to determine if the signal repeats. A true planetary transit will recur like clockwork on an orbital period. A signal caused by a star spot will also repeat, but on the star's rotation period, which is a crucial distinction. For signals that don't repeat, the next step is to employ a technique called multi-site observing. By using telescopes at different longitudes around the globe, astronomers can maintain a continuous watch on the star, ensuring that a fleeting event isn't missed and that any event detected is seen by multiple independent instruments, ruling out local interference or instrumental glitches. For the radio signals, the process is even more rigorous. Any candidate must be observed to exhibit a Doppler shift consistent with an origin outside our solar system, and it must be detected at multiple telescopes to eliminate the possibility of a stray satellite or terrestrial radar bounce. Despite the tantalizing possibility, the consensus among astronomers is that the anomalies from Tegodden star are almost certainly natural in origin. The star's well-documented activity provides a ready-made explanation for most, if not all, of the observed quirks. Yet, the system remains a prime target for future observation. Its proximity means it is an ideal candidate for direct imaging missions in the coming decades, which might one day be able to analyze the light reflected off the atmospheres of its planets, searching for biosignatures like oxygen and methane. The story of the Tegodden star anomalies is not one of disappointment, but of a new, more sophisticated era of SETI. It demonstrates that the search is no longer just about listening for powerful, deliberate beacons. It is also about sifting through the faintest of whispers, the subtlest of anomalies, in the most promising of neighborhoods, all while maintaining a disciplined understanding that the universe is filled with natural phenomena that are, in their own right, mysterious and wonderful. From the singular, electrifying shout of the wow signal to the complex, rhythmic heartbeat of a distant blazar, each of these 25 mysterious signals has fundamentally reshaped our understanding of the cosmos. They are not merely anomalies, they are profound teachers. The Lorimer burst taught us to look for entirely new classes of cosmic explosions, while the patient, erratic chatter of FRB 121102 proved that some of these events can and do repeat, dismantling our theories of one-time cataclysms. The clockwork precision of FRB 180916 revealed the gravitational dance of binary systems on a colossal scale, and the nearby blast of FRB 2020-00120E gave us a front-row seat to the awesome power of magnetars. We've learned humility from false alarms and clever hoaxes, from the Puritans born in a microwave oven to the tantalizing but terrestrial whispers from stars like HD 164595 and Tau Booties. Each of these episodes honed our scientific process, teaching us to first rule out the mundane before claiming the extraordinary. The deep, chaotic dimming of Tabby's star, while likely a colossal swarm of dust, expanded our imagination and demonstrated the incredible power of public engagement in science. Meanwhile, the Arecibo response, a human-made marvel in a field of wheat, reflected our deepest yearning for connection back at us, a beautiful piece of art born from our own hope. These signals collectively paint a picture of a universe that is far more dynamic, violent, and inventive than we ever imagined. They show us that nature is capable of engineering phenomena of breathtaking power and complexity, from the intense magnetic fury of a newborn magnetar to the slow, processing wobble of a jet from a supermassive black hole. They have moved the search for extraterrestrial intelligence from a simple hunt for a clear hello into a sophisticated field of astroarchaeology, where we must now sift through the faintest of whispers and the subtlest of anomalies, all while navigating an increasingly crowded radio spectrum of our own making. The journey is far from over. Each answered question raises a dozen more, and every new telescope, like the prolific CHIME array, unveils thousands of new bursts, building a statistical map of the high-energy universe. The search continues, not with disappointment, but with renewed vigor and sharper tools, driven by the enduring and human hope that we might one day find a signal that refuses to be explained away. So we want to hear from you. After this journey through the echoes of the cosmos, which of these 25 signals captured your imagination the most? Was it the tantalizing mystery of the wow signal, the rhythmic pulse of a gamma-ray heartbeat, or the chaotic beauty of a stellar dust storm? Share your thoughts in the comments below, and if you're fascinated by the endless mysteries of space, be sure to subscribe and hit the notification bell so you don't miss our next exploration into the unknown. The universe is still whispering its secrets, and together we can continue